just do the same exercise. So all the 15 instantaneous centers are shown. So here 1, 3 will be quite far away, so we need to choose, and 1, 5 also will be quite far away. So all the remaining instantaneous centers you can locate within the closer to the mechanism, on the mechanism. Okay. After that, then you need to calculate the velocities for joint A, B, C, and D's using IC's method. So let us say the dimensions are there. You need to measure the A instantaneous center 1, 3. So we need to measure B instantaneous center 1, 3, C to 1, 3, and C to 1, 5, and D to 1, 5. So only you can see the instantaneous center 1, 3 and 1, 5 are more important here for calculation purposes. Okay. After that, okay, this is how the dimensions are shown. Okay. So from A to instantaneous center 1, 3 and C to 1, 3, then yeah. Okay, then calculating the velocities for joint A, joint B, then joint C, joint D. So then calculating the angular velocities. Omega 2 is given to you, so you are calculating omega 3, then omega 4, omega 5. So you can see the calculations are very simple here. Okay, so the entire acceleration analysis, velocity analysis by IC method, all the calculations are here. So the only formula you are using is V is R omega, or omega is V by R. So you have to link whether you are referring to point A or point B or point C, point D. Alright, so after that then you tabulate your results, because you are doing velocity by a graphical analysis method and also instantaneous centers method. So you can come out with a comparison table like this, So you can see in this scenario you may be getting exactly the same values.
So the omega 2 is normal RPM to radians per second.
Yeah, you have to always convert the RPM into radians per second. Because for calculation purpose, the unit should be in radians per second. Angle should be in radians per second. So this is your part 4 of your assignment. Because part 4 of assignment 1 is the velocity analysis by IC's method. Now part 3 is the acceleration analysis. Okay. So acceleration analysis is very similar to the velocity polygon method. Okay, so we know that I just linked only 2 points, A and B, let us say. A, B. So this is position A, position B. Okay. So this will be position B to A. Right? So because you are referring A and B with reference to the global coordinate system. So this is your global coordinate system. So position A, RA, position B, RB. So now point B is referred from point A. So position of B to A. So vector addition we can write now. The position B can be written as position A plus position B to A. Okay. So similarly, velocity you can write it as velocity B vector is velocity A vector plus velocity from B to A vector. Okay. So now we can also write like acceleration of B is to acceleration of A plus acceleration of B to B. So this is very similar to your velocity, relative velocity method. But now when you are dealing with acceleration of B, so you have both normal component and tangential component. For example, let us say a simple link. Okay, this is, let us say, link 2. Okay, so this link is, let us say, is in rotation. Okay, so link 2 is in rotation, so with angular velocity omega 2 actually. Now this will have a, now this link, the path of the link you can visualize like a circular. So this you can visualize like a circle. Right? So if you recall your engineering dynamics, so now this one will have two components. So one component is the tangential acceleration, which is perpendicular to the link. So which is like this, tangential acceleration. And the other component of acceleration is perpendicular to this, that is normal acceleration. Okay, so this point will have two acceleration components. One is the tangential acceleration, which is perpendicular to the link, 90 degrees to the link. So the other acceleration is in the direction of the link. Okay, so it is in the direction of the link. So here you can write now acceleration of A bar, you can write in vector notation. So the tangential acceleration plus the normal acceleration. So normal acceleration, you know the formula is normal acceleration is magnitude. Magnitude of normal acceleration is so v square over r. R means the length of the link. So v is just the velocity of any point. So we can write normal acceleration like this. So any point on the mechanism, so we will have a normal component of acceleration and a tangential component of acceleration if the point is rotating. Okay. Now, for example, slider. So slider is not rotating, but it is only moving in a particular horizontal direction or along the incline. So the slider will have only tangential acceleration. So there is no normal acceleration. So if there is a slider, so it has only tangential acceleration. Okay, so now the formula which we have written, acceleration of B is equal to acceleration of A plus acceleration of B. So now when we apply this, so acceleration of B has both tangential component and normal component. So we can now write this as acceleration of B tangential plus acceleration of B normal should equal to acceleration of A tangential plus acceleration of A normal, okay, plus acceleration of B to A tangential plus acceleration of B to B normal. So we have 6 components. Now, for acceleration analysis, so for acceleration analysis, by the time we start acceleration analysis, okay, for a 4-bar linkage mechanism, for a 4-bar mechanism, so when we start four-bar linkage mechanism for acceleration analysis, we know the length of four links. We know A, B, C, D. We know theta 2, we know theta 3, we know theta 4, we know omega 2. Okay, we know velocity of A, we know velocity of B, we know velocity B to A. In addition to all these things, we also will be given angular acceleration alpha 2. So angular acceleration of link 2 will be given. So that means we know what is the angular acceleration of link 2. So similarly, if you recall, when we did the position analysis, we knew theta 2, the orientation of link 2. When we do velocity analysis, we know angular velocity of link 2. So similarly, when we are doing acceleration analysis, we know angular acceleration of link 2. So alpha 2 can be given clockwise or counterclockwise. So clockwise is negative, counterclockwise is positive. So angular acceleration alpha 2 is known. Then what are the things we need to calculate? So we need to calculate now acceleration of A. We need to calculate the acceleration of B to A. Then we need to calculate angular acceleration of B. Angular acceleration of link 3. Angular acceleration of link 4. Okay, so we need to find out acceleration of A, acceleration of B to A, then acceleration of B, then angular acceleration of link 3, angular acceleration of link 4. So these are the four. Okay, acceleration of A is very easy to calculate. So B to A, acceleration of B, angular acceleration of link 3, and angular acceleration of link 4. So these are the things we need to calculate when we are dealing with a 4-bar linkage mechanism.
So how to calculate tangential acceleration?
Yeah. So I'll continue with that. Now the problem is clear now. So for a 4-bar linkage mechanism, when we start acceleration analysis, we know all this data. We know length of the 4 links. We know the orientation theta 2, theta 3, theta 4. We also know angular velocity omega 2. And because we have done velocity analysis, so we know velocity A, velocity B, B to A, and also angular acceleration is given alpha 2. In addition to that, we also know the angular velocities of link 3 and link 4. Omega 3 and omega 4 also we can calculate by from velocity analysis. Okay, so all this information we know, so we need to calculate the acceleration of point A, acceleration of point B to A, then acceleration of B, then angular accelerations of link 3 and link 4. Okay, so now I'll go back to the formula. So acceleration of B tangent plus acceleration of B normal is equal to acceleration of A tangent plus acceleration of A normal plus acceleration of B tangent plus acceleration of, so this is BA tangent plus acceleration of BA normal. Okay, so this is the guiding equation for us. Now from this equation, what are the things we know? So what are the things we know? Because angular acceleration alpha 2 is given. Okay, so therefore you can calculate what are the okay, so we know that normal acceleration is d square over r, right? So now all the normal components here, okay? For example, acceleration of v normal. So v normal we know because we know velocity. Okay? So v d square over O4v, the length of link 4. So from there you know both the magnitude and direction M and D known. Okay, so let me just draw the mechanism like this. So link 2, let us say link 3, let us say link 4. Okay, 2, 3, 4. This is O2, O4. So since acceleration of link to angular acceleration alpha 2 is given, okay? So once it is given, then you can find out the magnitude of the tangential acceleration and the normal acceleration for this. Okay, so that means you know tangential acceleration magnitude, you know direction. So normal, you know magnitude and you know direction. So the magnitude is simply d squared by r. So velocity of a square, the r is the length of this thing. And the direction is in the direction of the link O2A. So you know the normal tangential is perpendicular to the link direction. Okay, so the magnitude is simply alpha into r into omega. So we know that v is equal to r omega, then a tangential is equal to r into alpha. So you know this s is equal to r into theta. So you know these equations from your engineering dynamics. So s is a linear variable, v velocity linear, acceleration linear. So theta is angular displacement, omega is angular velocity, alpha is angular acceleration. So for this point, because alpha is given, alpha 2 is given, so VA tangent will be, I'm sorry, alpha A tangent will be, so O2A into alpha 2. Okay? This one, I should write acceleration of A. Okay, acceleration of A normal will be velocity A square over O2A. So that means for point A, you know what is the magnitude and direction of the acceleration of A tangent, and also the magnitude and direction of the normal component. So that means you know the complete information of this motion. So this is known. Okay. So similarly, VA tangent you know because you know angular velocity of link 3. Okay. So now VA tangent direction known. BA tangent direction will be known. Okay. Then acceleration of BA normal. So both magnitude and direction. Okay, so BA normal, you know velocity of BA. Okay, so velocity of BA square over AB, the distance, that gives you the normal component magnitude. So the direction will be in the direction of BA because you're already plotting the mechanism to scale. So therefore you know the BA normal direction. So BA normal direction will be like this. So this will be acceleration of BA normal. So BA tangent will be perpendicular to this. So BA tangent, you know the direction for BA tangent. Now acceleration of B tangent also you know. So acceleration of B tangent will be perpendicular to the link form. So this will be acceleration of B tangent. Then acceleration of B normal will be like this. Okay, so that means acceleration of B normal, you know both magnitude and direction. Acceleration of B tangent, you know the direction of it. You know the direction. You need to find out the magnitude. Okay, so you need to find out the magnitude. So similarly, BA tangent, you know direction. Okay, you need to find out the magnitude. And BA normal, so you know both magnitude and direction. So you know magnitude and you know direction. Okay, so that means when you start acceleration analysis, okay, the guiding equation will be similarly acceleration of B is acceleration of A plus acceleration B to A. But when you're dealing with acceleration, so there will be normal component and tangential component. And normal component, both magnitude and direction we can calculate. Because we know the velocities, so therefore the magnitudes of normal components we can calculate. And the directions will be because we already know the orientation of all the links. So the normal will be acting in the direction of the links. So therefore you know for acceleration of B normal, both magnitude and direction normal. Acceleration of BA normal, both magnitude and direction. Now for the point A, for the point A, we know both direction and magnitude for both the tangential component and also the normal component. So that means for point A, we have complete information. For point B, normal, we have complete information. Tangential, we know the direction. So the tangential for B will be perpendicular to the link form. Okay, so this is the direction of acceleration of the tangent. So this is just like velocity. Okay, so you know the direction. The magnitude AB normal, we know AB normal is simply VB square over O4B. Because we know velocity B when you are starting acceleration analysis. So therefore you know the magnitude of the B normal and also the direction. So now you have to plot the same thing. Just like the velocity polygon, now we draw acceleration polygons out the magnitudes of acceleration of B tangent and the magnitudes of acceleration BA tangent. So this is basically the theory. Anything not clear, let me know. I'd like to do once again. So it is simply acceleration of B normal. Okay. First I write tangent plus acceleration of B normal. Okay, so this is the guiding equation. Okay, so from this you know both complete information, you know. Because acceleration of A tangent will be O to A into alpha 2. Okay, so direction will be perpendicular to the link. So acceleration of A normal is okay, VA square over O2 A. So we know both direction and magnitude of the normal. So point A, you know complete information. Then BA tangent, direction normal. Then BA normal. So both magnitude and direction. So magnitude plus direction. So B normal, we know both magnitude and direction. So B tangent, you know direction. Okay. Okay, direction normal. So that leaves us to calculate only the magnitude of B tangent plus the magnitude of BA tangent. So this one we can plot like a, just like velocity triangle. Now we are going to draw acceleration triangles. Okay. Now everything to be to the scale. So B tangent, direction known, magnitude find out. B normal, both magnitude and direction known. Okay, so A complete you know, BA you know, direction, we need to find out the magnitude. So here you know both magnitude and direction. Alright, so now I just go through the slides, and the slides will tell you the same thing. So this is just to reinforce your concept. Okay? I'll come to this slide. So you can see here a simple link in rotation. So this is just a simple link. Okay, a simple link in rotation. So now you can see, consider this is the point P. So you are referring this point P to A. Okay. So the acceleration of the point P with reference to A has two components. One is the tangential component and the other one is the normal component. So the net acceleration will be the addition of these two vectors. So this is the direction of acceleration P to A. Okay. But the two components are tangential, will be perpendicular to the link. Okay. Again, depending on the direction of angular acceleration alpha 2. Okay. So if PA is shown upwards, means the acceleration is counterclockwise, as shown here. Okay. If the acceleration is downwards, then the PA tangent will be the other side. Okay. So essentially, you can see from this slide that a simple link in rotation has acceleration, which is divided into two components, a normal component and tangential component. Now the direction of the tangential will be perpendicular to the link. Again, whether it is alpha 2 is clockwise or counterclockwise. If it is counterclockwise, PA tangent is perpendicular upwards as shown here. If alpha 2 is the other side, then PA2 will be like this. Then normal will be always in the direction of the link. Okay, so you know the normal direction, PA tangential direction. So PA magnitude will be simply AP into alpha 2, the magnitude of tangential acceleration. Then the magnitude of normal acceleration will be velocity of PA square over P. Okay, so so this one is the normal component, so this one is the tangential component. So you can see the vector addition here. Okay, so acceleration of PA is as shown here. I skip this. Now let us look here. This figure you need to understand very clearly. So you can see the 4-bar linkage mechanism, right? So this is link 2, link 3, link 4. So the ground is the link. 4 to 4 is your ground link. So theta 2 is the orientation of link 2. Now point A focus here. Okay. Now angular acceleration is given. Now you can see clockwise. Alpha 2 is given clockwise. So therefore the tangential acceleration is now, you can see it is shown perpendicular to the link in the direction of angular acceleration. Okay, so the normal component will be in the direction of the link. Okay, towards O2, from A to O2. So always you know complete information of point C. Now come to point B. Okay. So come to point B. So here B to A, okay, acceleration of B to A, tangential will be perpendicular to the BA. Okay. So BA tangent will be as shown the line QQ here. So the line QQ is the direction of acceleration of BA tangential component. Okay. Then acceleration of BA normal will be the direction of BA. Okay. So BA normal will be in the direction of BA. Now look point B. So on link 4, so acceleration of B tangent will be perpendicular to link 4. So AB tangent is the line PP. So you can see the line PP here. So that is the direction of acceleration of B. Okay. So that is this PP line. So focus PP line and QQ line. So PP line is the direction of acceleration of B tangent. So this QQ line is the acceleration of BA tangent direction. Okay. So I told you how to calculate the magnitudes. Magnitudes because we know velocities, so magnitudes we know. Now this is the direction of acceleration of B normal. Okay, in the direction of link BO4. So now we need to plot the mechanism, plot the acceleration components to scale. So when you do this, now we know point A, complete information. So we know acceleration of A tangent and acceleration of A normal. So just take a reference coordinate axis. Now in this example, the plot started from this point here. Okay, so you know acceleration of A tangent, magnitude you know, and also acceleration of A normal, magnitude you know. So first we'll draw the vector acceleration of A tangent. You can draw this because you know the direction, you know the magnitude, acceleration of A tangent. Now from the tip of this, you draw acceleration of A normal, because you know the magnitude and direction of acceleration of A normal. Now the black line basically just addition of these two vectors, so that tells you the acceleration of A. Okay, so that is the acceleration of A. So what we are doing is, so I'm just trying to draw here. Okay, this is not. Okay, so we choose a coordinate system. Okay, choose a scale factor. Now acceleration of A tangent we know. So we just draw acceleration of A tangent. Now from the tip of this, okay, we draw acceleration of A normal. We know both magnitude and direction. Okay, so as shown there, so acceleration of A normal. So it is drawn like this. So this is acceleration of A tangent. So this is acceleration of A normal. Now the equation is that you have acceleration of B tangent plus acceleration of B normal is equal to acceleration of A normal of a tangent plus acceleration of A normal. Then plus we need to get BA tangent and BA normal. Okay, I think this is done. Okay, so never mind. So you can see from the tip of this point. Now this is your acceleration of A vector. Okay, so that means we have drawn this complete. Now you are adding this BA tangent and BA normal. But BA tangent we don't know the magnitude. But we know BA normal, direction and magnitude. So from the tip of acceleration of A, you are drawing the BA normal, both magnitude and direction. Okay, so you draw BA normal, both magnitude and direction here. Okay, so you have completed now this side. So we have completed this side. So BA tangent will be perpendicular to this point. Okay, so BA tangent will be perpendicular to this point. So now from the origin, you know acceleration of B tangent direction. Okay, now from BA normal, so you know acceleration of B normal, both magnitude and direction. B normal, both magnitude and direction. So overall you can complete this triangle, polygon, then you will be able to calculate the magnitudes of B tangent and BA tangent. So BA tangent is shown here, B tangent is shown. When you do the example, then you can understand. So I'll just skip this. Okay, now let us see, this is the easy thing to understand first. Now this is the point A. So the angular acceleration direction is shown. So alpha 2, the direction is shown. So therefore you know the acceleration of A tangent, magnitude and direction, and the acceleration of A normal, magnitude and direction. So you are drawing acceleration of A normal and tangent. So you have completed this, okay? Now come to point B. So this B is the slider, so the slider is only moving horizontally. Okay? So acceleration of B has no normal component, it has only tangential component. So from here, so you know you are just drawing the acceleration of B direction. You don't know the magnitude, but you know the direction is horizontal from the horizon. Okay? So now we know we have plotted A normal, A tangent, so you are here now. From here now you draw BA normal, so BA normal, you know both magnitude and direction. Okay? So direction is this, link AB, then magnitude is VBA square over AB. Because we know velocity BA, therefore we know BA normal. So that is this. Now BA tangent, you know the direction. BA tangent will be perpendicular to AB. So this is AB. So BA tangent is perpendicular. Okay. So now from the tip of BA normal, because you follow this expression, okay, we have drawn acceleration of A tangent and normal, and BA normal we have drawn. Then BA tangent, the direction we have drawn. Now these two lines will intersect at one point. Okay, acceleration of B direction line or BA tangent line, so both intersect at a point, and from the intersection you will be able to measure. Now this will be the magnitude of acceleration of B, and from here to here will be the magnitude of BA tangent. Is that clear, or any questions?
So,
Always start from the point where you know the maximum information, and that is always point A. So that will be always point A. So you need to choose a coordinate axis, then you start acceleration of A tangent, acceleration of A normal. Now from the tip of this, you need to draw BA normal, you know, then you only know BA tangent direction.
so technically before that you did drawing line below the here for the tangential for
BA tangential direction we know BA
you don't know
normal.
the magnitude.
Huh?
The magnitude
BA tangent magnitude we don't know. So that is what you can find out from here.
wait, so which one are we finding out? The tangential for BA and magnitude, right?
In this case, B has no normal component. So it is only acceleration of B. Okay, so that means it has only tangential component. So that is what you can read from. So like this, once you start doing some examples, then you can understand. Okay, the assignment part first I go through, then we can go through some examples. So the assignment part, you have to do the graphical acceleration analysis as part of your question 3 of assignment 1. So question 4 we have already done the IC's method. So question 3 you can prepare some headings like this. Okay. So this is your mechanism. So on the mechanism you need to identify first the directions of all the components. For example, this is the point A, right? So alpha 2 is given as counterclockwise here. So the tangential component is as shown here. The normal component is as shown in the direction of the link. Okay, so you first show your 6-bar linkage mechanism drawing and then identify the directions of all the pin joints, normal and tangential components. Okay, for example, this point D has only normal acceleration, tangential acceleration. It has, because the slider is moving horizontal, so it has no normal component. Okay, so here this is the angular velocity of link 3, which you know. Okay, if you see this point B, okay, so this point B is on link 4, so this is your link 4. So B normal is shown here. So this is B normal. So B tangent is perpendicular to the link as shown here. So B tangent, you only know the direction. So B normal, you know both magnitude and direction. Now if you see this one is BA normal. So BA normal, you know both magnitude and direction. So BA tangent is the perpendicular to BA. So this is the direction BA. So you know BA tangent directionally. So you can now link it, point A and B. Okay. So similarly, you can see just here the point C. Okay. So CA. So this is normal, CA normal. Okay. CA tangent, you know the direction, perpendicular to CA. Okay. Now this is CD. Okay. So you know CD tangent also, perpendicular to CD. So that is CD tangent. So like that, for all points, identify the normal and tangential components for all the pin joints. Okay, now you are linking joint A and B. So this is point A, point B. Okay, so you are linking A and B. So we write the same equation as shown here. So we write the same equation. So normal component of point A. So how you can calculate? So OA, that is length of your link 2, and angular velocity square. Okay. So R omega square. Okay. So you know the magnitude and direction of the normal component. So the magnitude is now 677.655. What will be the direction? So the direction will be as shown. This is the direction. Okay. Now tangential component. So OA into alpha 2. OA is the length of link 2, we know. Now in this case, acceleration of component 2 is given, link 2 is given 0. So therefore it has no tangential component. So if you read your question, so I think it asks you constant angular velocity. So constant angular velocity means the tangential acceleration, angular acceleration is 0. Now for normal component of B, point B, so it is point B is on link 4, so you can calculate as B into omega 4 square. So you know the magnitude of the normal component of point B. Then you can calculate acceleration BA normal component. Okay, so it is AB into omega 3 square. So then these are the angles. So normal component of acceleration of A angle is 240 degrees. Then normal component of acceleration of B is 250. So similarly, so you can measure all the angles from your drawing. After that, then complete the acceleration polynomial. So your guiding equation is acceleration of B normal plus acceleration of B tangent is acceleration of A normal plus A tangent, then plus BA normal and BA tangent. Okay, so here you are taking the So this is the coordinate axis shown. So you can see this is the normal component of acceleration of A. Then from the tip of this, okay, tangential component is 0. So you have only normal component of acceleration of A. So from here you are drawing the BA normal. BA tangent is drawn. Okay, this is BA tangent. So what is BA normal? So BA normal is negative of 9. So BA normal is shown like this. Okay, from this point BA tangent is shown. So from here BA normal, then BA tangent. So you only know the direction of BA tangent. So from this point you just draw this constriction line BA tangent. Okay. Now acceleration of B normal you are drawing. Okay. So this is the line. So from the tip of this B normal you draw the direction of B tangent. So these two will intersect at this point. Okay. So you can now read from this, okay, the magnitude of B tangent as shown here, then BA tangent magnitude. So you can list those values. So from these values you can convert based on the scale factor into the magnitudes of the accelerations. So the directions you can measure from your drawing. So this is your drawing for point A and B. So you are linking point A and B. So joints A and B. First calculate all the information, then the orientations of all the accelerations known, then complete your acceleration polygon. So how to draw? So this will be your guiding equation. Acceleration of B normal plus B tangent should equal to acceleration of A normal plus A tangent plus BA normal plus BA tangent. So you have to just follow. Okay. So choose coordinate axis. First draw point A information. Then from the tip of point A, draw BA information. Then go back to the horizon. Then draw point B information. So you should be able to complete the polygon. Then from the polygon, the unknown quantities can be calculated. So in this case, it is BA tangent and BA B tangent. Alright. So next you can move on to, okay, this is the calculation part. Next you have to move on to, okay, this is how to calculate alpha 3 and alpha 4. So if you know BA tangent, okay, so BA tangent over AB gives you angular acceleration of length 3. Okay. So then you know B tangent, so B tangent over B, the length of link 4, that gives you angular acceleration of link 4. So once you calculate, once you complete the velocity polygon, okay, as is shown you, the equations are always quite simple here. For any point, you know, you can say so acceleration of A, right, tangent. So this is O to A, alpha to no. Acceleration of A normal. So you can either use VA square over R, or we know VA is R omega, right? So you can also use this as R omega 2 square. So that means you can also use O to A omega 2 square. So here, AT is R O to A into alpha. Now, if you know here, let us say you know A2, you know O to A, alpha is unknown. So you can always write alpha is acceleration of T over O to A. Now, when you know acceleration of BA tangent, okay, so let us say you know this from acceleration polygon, okay, known from acceleration polygon. So if you know BA tangent, then you can easily calculate what is the angular acceleration of link 3. So angular acceleration of link 3 will be acceleration of BA tangent over AB RBA, the length of link 3. So similarly, you can calculate acceleration of link 4. So point B is on link 4. So this will be acceleration of B tangents over O4. So that means if you know the tangential components, then you'll be able to link those to the accelerations of the links. The points you can find out from the polygons. So by drawing the acceleration polygon. So,
So,
yep.
can you show us how to draw the polygon step by step?
Yeah, sure. Okay, first I touch upon assignment, and this file is on Canvas. So I have already uploaded, so you can download. So then you find out linking for joint C. So for joint C, this is the guiding equation. So now acceleration of C is acceleration of A plus acceleration of CA. So you are linking point C and A. So then you will be drawing another acceleration polygon, then you can calculate the unknown things, then join D. Now this is your linking point C and D. So acceleration of C is equal to acceleration of D plus acceleration CD. So you need to draw another acceleration polygon, then find out the unknowns. After that, you need to just list all the values. Okay, so that completes. So alpha 2 is given as 0. So you are calculating angular accelerations of link 3, link 4, link 5, and okay, all this data, both normal and tangential components. All right. Okay, this is okay. Later, once you do your working model simulation, okay, so you can see, just create your working model, okay, create all your parameters, okay, so your velocities, then your accelerations, then your forces, okay, identify all the points. So before you simulate, okay, you need to show your screenshot like this. So before you simulate, so once you simulate, okay, then you can see the values, whatever the values you get for a particular orientation of 60 degrees, then you can compare with your calculated values. Only that. This portion, there is no need to do for assignment 1, but this will be for assignment. But I just included this so that it gives you some idea what you need. Okay, so this is the assignment part. Okay, so what are the steps you need to do? So you can just have a look at this example. So this is about a 4-bar linkage mechanism. So what is the data given? So you can see the length of link 1 is given, link 2, link 3, link 4. So theta 2 is given, omega 2 is given. So this is the position vector A. So this is delta 3 is given. So this is basically the shape of the mechanism is like this. Okay. So theta 2, delta 3 is given. Okay. So you need to first PA is this vector. So this is your link 3, link 2, link 4. Okay. So omega 2 is given. Okay. Theta 2 is given. So you can find out theta 3, theta 4 by position analysis. So after that, then you have to do the acceleration analysis. So this is mainly for the velocity analysis. Okay, so I showed you. Okay, you may note down this data. So the length of 4 links, theta 2, omega 2. So in this case, angular acceleration is given as 0. So the PA vector is 6 and delta 3 is 30 degrees. So first, just note down the numbers. Note down the numbers, and the figure I'll show in the next slide. So this is the figure. Just note down the numbers only. So then you need to plot the mechanism to scale to find out the velocities. Okay, so you need to find out velocity of free velocity, okay, point B, then angular velocity of link 3, angular velocity of link 4. So that means if you want to start doing for this, you need to calculate velocity for the point B, angular velocity of link 3, angular velocity of link 4. Okay, so let us say given, consider angular velocity of link 3 is given. Okay, so you can take this as negative 5.991 radians per second. So consider that you have done velocity analysis and you got the angular velocity of link 3 as 5.991 radians per second. So the negative sign only indicates that it is clockwise. So similarly, omega 4, your done velocity analysis, the value is negative 3.992. So that means you know this additional information from velocity analysis. After that, you need to now you are doing acceleration analysis, right? So we link point B and point A. So we can write acceleration of B tangent plus B normal is equal to A tangent plus A normal plus BA normal, BA tangent, BA normal. So what is the acceleration of B normal? So B normal is, so the link 4 into omega 4 squared. So link 4 is given, what are the dimensions given in 4? So link 4 is 9 inch, okay? Omega 4 you calculated as 3.992. So use both, calculate. Acceleration of B normal, you're calculating as link 4 multiplied by the omega 4 squared.
So this is the electric part.
This example I said no. It is not included. I put only up to assignment. This I'm supposed to do for the next session. Okay. So here you are just calculating B normal. Okay. Then the orientation of this, how do you know? Okay. So you just see. So this is the point, right? So the direction of B normal will be in this direction. Okay. So from B to O4. So the orientation of that, you know theta 4 already. So you can calculate this as theta 4 plus 180 degrees. So this is the direction of the orientation of B, normal component. So orientation of B, normal component direction. Next, acceleration of A, normal component. So this is length of link 2 multiplied by omega 2 squared. Okay, so omega 2 is given to you. So therefore, A also you know. So you know A is given as link 2, right? 2. Omega 2 is 10. So 10 square is 100, 100 into 2, 200. So you know the magnitude of normal component acceleration for point A. So for point A, normal component acceleration, you know. Then the orientation of normal component acceleration for point A. So point A, the direction will be like this, right? So in this direction, A to O2. Okay? So how do you get this direction? You already know theta 2. So, so this will be theta 2 plus 180 degrees. So that is, you know the direction. So similarly, the tangential component of point A acceleration. So this is r into alpha 2. Alpha 2 is given 0, therefore it has no tangential acceleration. Point A has no tangential acceleration. Now we calculate acceleration of BA, normal component. Okay, so acceleration of B normal component is B into AB into omega 3 square. Omega 3 is the angular velocity of link 3. Okay, so you calculate the magnitude, then the direction also you know. So from the dimensions given, so you know the direction of BA normal. So BA normal will be from B to A. So now from omega 3, omega 4, we calculate all these values. So once you do this, so the guiding equation is the acceleration, relative acceleration equation. So then you need to plot the mechanism to scale. So when you plot the mechanism to scale, so you follow from the starting point here, okay? So you choose appropriate scale here, okay? So acceleration of A, you know, if you see acceleration of A is 200, the direction is 210, okay? So the direction is 210 and the magnitude is 200. So when you plot from the here, so this is the 200 scale acceleration of A. The direction is 210 degrees. So you are just plotting acceleration of A because you know magnitude and direction. Now from the tip of this, so you are drawing BA normal. So you know BA normal, the magnitude is 251. The direction is also you know. Okay? So therefore from the tip of A, you are drawing BA normal. Okay? Now BA tangent will be perpendicular to BA normal. So you just draw a perpendicular line from the tip of BA normal. So this dotted line is just the perpendicular. So you can draw up to here, right? So first we start from the origin, we draw acceleration of A. Okay? So from the tip of acceleration of A, we draw BA normal. So BA normal we can draw because we know both magnitude and direction. Now from the tip of that, we need to draw BA tangent. So BA tangent is simply perpendicular to BA normal. So we don't know the magnitude, so just draw a line, dotted line from the tip of BA normal. So we just draw a dotted line. So now we have completed, if you see, we have completed this portion of the equation. So we have completed A tangent, normal, BA tangent, BA normal. So now we have to draw the other side. So the other side means, so now you start from here, okay? So we know B normal, both magnitude and direction. So we draw B normal from here to here. So from B normal, we know only the tangential direction, which is perpendicular. So just draw a perpendicular line from B normal. From the tip of B normal, draw a perpendicular line. Now the two lines, so the dotted line here, then the dotted line from BA tangent will intersect here. So that you fix. Okay, so now you know from here to here is AB tangent. Okay, so from here to here is BA tangent. So you can read from your drawing, so the value of BA tangent and the value of B tangent. Okay, so these are the two things missing, so you can calculate these two. Is this clear?
So the direction you just follow from the other diagram, right? Or the degree 210 degrees you take anti-clockwise always, or the A.
Okay, so always from here. Okay, so if this is theta 2 is this is the angle, right? But your normal is in the opposite direction. So you have to add 180 degrees to this. Okay, so theta 2 is this direction, but your normal is in the opposite. So theta 2 plus 180 degrees. And BA is this direction. So you know AB, right? So you just add 180 degrees. You will get BA. No, otherwise once you have the figure, you can just measure also, you know. Okay, so this is how the acceleration polygons are drawn. So always, so this is the guiding equation. As I said, for point A, always you know the complete information, both magnitudes and directions, normal and tangential components. If you're lucky, sometimes the normal component will be 0, so your drawing will be simpler. Okay, so otherwise, you just fix your coordinate axis, then start drawing first point A. Complete both normal and tangential component. Okay, so then from the tip of the acceleration of point A, then draw BA normal. Because BA normal always you know the magnitude and direction. Then from the tip of BA normal you just draw a perpendicular line, dash, dotted line. So this is the dotted line you are drawing from BA normal. Up to this you will have no problem in drawing. So BA tangent, BA normal will be perpendicular to each other. So just from the tip you draw a dotted line. Now you go back to B, okay, draw acceleration of, okay, this is B normal. Now B tangent will be perpendicular to this. So from the tip of this, draw a perpendicular line, a dashed line. So both will intersect at this point. So this one you can learn if you draw yourself. Any doubt or anything which is not clear? When you do acceleration analysis, you need to calculate the normal components magnitudes. Okay, so all the normal component magnitudes you can calculate. And you know the directions of normal components. So the only two missing components would be the B tangent and BA tangent. Normally, the story will not end here. Okay, so you may be asked to find out at different points on the linkage to find out the accelerations. Okay, so let me just check whether you can do a simple example, because any problem will take more than half an hour to complete. We have a simple problem if you do. Now, can you note down the values first? So, link 2, link 3, outside theta 2, omega 2 is given, alpha 2 is given. Okay, angular acceleration is 0. Okay, the mechanism is as shown. I think you plotted this already earlier. Anybody not scanned, let me know. So, I think I have. Hey, you have not scanned, right? Who?
Jared.
Wrong.
Yes.
Who else? Chiam is there? No. Narayan Swami, no. Ganpati, no. Harivan. All right. Edmund, no. All right. So I will put this. So once you note it down, okay, this is the figure. So the direction of A tangent will be as shown here. So this is the direction of tangent. Okay, this is the BA tangent will be perpendicular because B is the slider. So the tangent will be perpendicular to this. Okay, then the direction of back acceleration of B will be horizontal. So that means B has only horizontal movement. Okay, so let us say your angular velocity, I think you have calculated earlier. So it is about negative 2.475. So you may take angular velocity of link 3 as negative 2.475. So then you can calculate these things. Okay. So you are linking, this is the point A, so this is the point B. So you are linking these 2 points. Okay. So you can write acceleration B is acceleration of A. So B has no normal component because it is only having tangential component. Normal component is 0. Okay. So you can write acceleration of B is A normal plus A tangent, BA tangent plus BA normal. So A normal you can calculate as O to A into omega 2 square. Omega 2 is given, right? So how much omega 2? 10. So 100 into 1.4, that is 140. So that is the magnitude of the normal component. Then the direction of the normal component will be, so theta 2 plus 180 degrees. So you know the direction of the normal component, 225 degrees. Then the tangential component of point A. So R into alpha 2. Alpha 2 is given 0, so therefore it has no tangential component. So BA normal is link 3 into omega 3 square. So we know we calculated omega 3 from velocity analysis multiplied by the length of the link, so you get the BA normal magnitude is 24.5. Then the direction of this will be 180.1. Okay, so now you know all the information. Now you have to plot the mechanism, velocity acceleration polygons. So how we start? So you choose an appropriate coordinate axis x and y here. Okay, so acceleration of A, you know both magnitude and direction. So you can plot this vector, acceleration of A. So from the tip of that, you know BA normal, magnitude and direction. So BA normal, you know both magnitude and direction. So therefore you draw this BA normal. Now from the tip of BA normal, you are drawing perpendicular line. So that line is just a dashed line. Because you only know the direction, therefore you just draw a dashed line. So that means, so you have completed this portion. We have drawn A tangent A normal, B A tangent B normal. Now you have to draw acceleration of B. So acceleration of B is now from the starting point you draw a line. Okay? So horizontal line, because B is the slider which can only move along x-axis. So these two lines, this line intersect here. So now you can fix the point. So this will be acceleration of B. So from your scale factor you can measure. Then this will be BA tangent. So you know both the magnitude and direction of BA tangent and B tangent normal. Okay. So then multiply with your scale factor, you will get the actual values. Is that clear? Always, it's you choose a coordinate axis, velocity falling, right? So let us say for point A, both normal and tangential. So tangential, this is acceleration of A tangential. So normal will be perpendicular to this. So you know the magnitude, let us say. This is your acceleration of A normal. Okay, now from the tip, if you know acceleration of BA normal component and magnitude, let us say you know, so this is, let us say your BA normal. Okay, so BA tangent will be perpendicular to this, so BA tangent will be like this. So now from the origin, you need to draw B. So this is A tangent, A normal. So this is BA normal, BA tangent. So now from here, let us say you know acceleration of B normal. So just draw B normal like this. So now from the tip of this, you draw B tangent. So now you can see these two lines will intersect. This is B tangent. And BA tangent. So this will be your acceleration of B tangent. So this will be your BA tangent. Alright, so I think next session we'll do 1 or 2 examples in the class. Next week means the next session. So next week is the study week. Alright, so we will just draw the polygons and follow the equation. So you know the magnitude and directions of all normal components. Only you need to find the tangential components of B and B. Yeah, we stop now.
IC 我大概啊